You've definitely seen an X-ray image before, right? A picture of your bones, or maybe something you saw in a movie. But have you ever stopped to think about how it's actually made? It's not just a fancy camera. Today, we're going to peek inside the incredible technology of the modern X-ray detector, the device that literally turns invisible radiation into a life-saving image.
Okay, so let's start with the biggest question of all. X-rays are these super high-energy particles, photons, that just fly right through most things. So how in the world do you build something that can actually catch them and make a picture out of them? That's the fundamental challenge we're going to unpack today.
At its core, every single X-ray detector has one mission, one job to do. Take one of those invisible X-ray photons and turn its energy into an electrical signal that we can actually measure. And you know, the better a detector is at this one job, the sharper and clearer that final image is going to be.
All right, here's our game plan. We're going to start with the most basic choice in detector design. Then we'll check out the workhorse technologies, look at the big revolution that came from silicon chips, and then put them all head to head. And finally, we'll get a little glimpse into the future. So if you want to build a modern detector, you have to make a choice right at the very beginning. And this one decision, it pretty much impacts everything else down the line. It's the choice between two completely different ways of doing things, direct and indirect conversion.
So here's the big difference, right? Direct conversion is this really clean one-step process. An X-ray hits the material and boom, you get an electrical charge. That's it. Indirect conversion, though, it's more like a two-step dance. First, the X-ray creates a flash of visible light. Then, a second layer has to see that light and turn it into the electrical charge we need.
Let's zoom in on that indirect path for a second. Step 1 is called scintillation. Basically, one super high-energy X-ray photon slams in and thousands of little visible light photons fly out. Then comes step 2, photodetection. All those light photons get captured by a silicon sensor, which finally creates the electrical signal we're after. But this whole two-step process has a built-in problem. See, those little light photons, they aren't guided. They just spread out in every direction, kind of like a tiny light bulb just flashed on inside the detector. This lateral spread is the #1 reason, the built-in reason, why indirect detectors can sometimes give you a slightly blurrier image.
Okay, so now let's see how these ideas play out in the real world with the workhorses of modern X-ray rooms, the flat panel detectors. You've probably seen these things. They're those big rectangular plates used in most digital X-ray systems today.
So, the first type of indirect panel used a kind of powdered scintillator called gadox, and this stuff forces engineers into a really tough spot. See, to absorb a lot of X-rays, you need a nice thick screen. But the thicker you make the screen, the more that light spreads out, which just kills the sharpness of your image. You're stuck. You have to pick one: good absorption or good sharpness. You can't have both.
But the solution they came up with is just brilliant. Instead of a powder, engineers figured out how to grow a different material, cesium iodide, into millions of microscopic, needle-like crystals. And these little columns, they act like perfect, tiny fiber optic cables, guiding the light straight down to the sensor with almost zero sideways spread. This completely breaks that trade-off. Now you can have a thick screen for great absorption and get a super sharp image. Genius!
All right, now let's jump back over to the other family, the direct conversion flat panel. The design here is just beautifully simple. It completely throws out the scintillator and the light sensor. It replaces that whole sandwich with a single elegant layer of something called amorphous selenium. This material is what's known as a photoconductor. It just turns X-rays straight into charge. And its defining advantage? Well, it's the complete elimination of that light-spreading step. There's no light to blur the image. Instead, a really strong electric field is put across the selenium, and it grabs that electrical charge the instant it's created and pulls it straight down to the pixel. The result is the sharpest possible image you can get, fundamentally.
So we've seen how flat panels are great for making these big detectors. But what if your top priority isn't size? What if it's raw, speed, and the absolute lowest noise possible? For that, we've got to turn to a whole different class of detectors, built on these perfect crystalline silicon chips. It's a really cool story of how one technology paved the way for its much faster successor.
For decades, the undisputed gold standard was the charge-coupled device, or CCD, and these sensors were amazing for their time. They produced these beautiful, clean, super low-noise images, but they had one massive Achilles heel. They were just so slow to read out the image.
And here's why they were so slow. A CCD reads out the image using what's called a bucket brigade.
Just imagine each pixel is a little bucket collecting charge. To measure what's in them, you first have to push every single row down by one, then you take that bottom row and you pass each bucket, one by one, past a single measuring station. Every single pixel has to get in a very long line and wait its turn. It works, it's very precise, but my gosh, is it slow.
Enter the successor, the modern CMOS sensor. The huge revolution here is something called an active pixel sensor. So instead of each pixel being a simple passive bucket, every single pixel on a CMOS chip is its own little sophisticated electronic circuit with its very own amplifier built right into the pixel itself.
And this active pixel design, it completely changes the game. No more bucket brigade. The charge gets converted to a voltage right there, inside the pixel. The whole sensor then basically acts like computer memory. The electronics can just instantly grab the value from any pixel at any time. This allows for what's called a massively parallel readout, which makes CMOS detectors just unbelievably fast. So fast, in fact, that you can do real-time X-ray video.
Okay, so we've met all the players, right? The indirect and direct flat panels and these new CMOS speed demons. So let's put them all side by side. Which one is actually the best? Well, as you might guess, it really depends on what you're trying to do. Let's break this down. If you're looking for pure spatial resolution, the sharpest image, the direct FPD is your winner, no question. By getting rid of that light spreading step, it just wins. Now, for low-dose performance, CMOS is the clear champion because its active pixel design creates the lowest electronic noise. And for speed, oh, it's not even a contest. The parallel readout of CMOS is just worlds faster than anything else.
So let's say your number one job is to see the absolute tiniest detail imaginable. You're going with the direct FPD every time. The physics of how it works just makes it fundamentally sharper. And this is exactly why it's still the gold standard for mammography, where being able to spot those tiny microcalcifications can literally save a person's life.
But what if you're doing a long procedure, like fluoroscopy, where the X-ray beam is on for a while? Well, now your top priority is patient safety, keeping that radiation dose as low as you possibly can. And here, CMOS is the clear winner. Its electronic noise is 2 to 3 times lower than a standard flat panel, which means it can make a really clear image using way less radiation.
But here's the thing. The story doesn't end here. The evolution of these detectors is far from over. In fact, we are right on the edge of the next great leap in X-ray tech, a shift that takes us beyond just measuring the total brightness of a pixel.
You see, every single detector we've talked about so far is what we call energy integrating. Think of it like putting a bucket out in a rainstorm. At the end, all you know is the total amount of water you collected. The future, though, is photon counting. This is like having a system that not only counts every single raindrop as it falls, but also measures the size of each one. It's a whole new level of information.
And the power this gives us is just staggering. First off, you can set a minimum energy level, and any signal below that, which is basically all your electronic noise, just gets ignored. Proof. It's a true zero-noise detector. And second, by sorting the photons into different energy bands, you get spectral information. This is literally the difference between a black and white photo and a full-color one, letting you start to identify the specific materials inside the body.
This new technology is going to take us way beyond just seeing shadows and into actually identifying what those shadows are made of. And that leaves us with this one last, really exciting thought. After more than a century of black and white imaging, what new medical discoveries are just waiting for us when our X-rays can finally see in color?